One piece of information can tell you a lot. Let me show you how. Welcome to this Quick Hits video. My name is Kevin Fiesel, and I am the proprietor of Catalaxy Services LLC, a consulting firm which specializes in work all across the data platform space, especially SQL Server. The inspiration for this Quick Hits video comes from a book I read earlier this year entitled How to Measure Anything. This isn't a review of the book per se, but it is instead my attempt to describe and recreate an interesting phenomenon. Join me in the classroom as we dig a little bit into statistics. Let me first explain this idea, then I'll talk a little bit about the math behind the idea, and finally we'll see it in action to demonstrate the counterintuitive result. One concept we talk about a lot in statistics is sample size. We often talk about how some statistic may be interesting, but we need a larger sample size to confirm that what the result indicates is real and not some ephemeral phenomenon. For a quick baseball example, let's say a batter is hitting 400. What does this tell us about the player's ability to hit the ball? By itself, not very much. See, there's a big difference between being Ted Williams and batting 400 over an entire season versus being a guy who went 2 for 5 in a single game. When Ted Williams batted 406 in the year 1941, he did so over 606 plate appearances and 456 at-bats. He sustained this over a long stretch of time in a wide variety of circumstances. Over that season, he erased any doubt of his being a great hitter because he performed an act so uncommon that, of the 39 players ahead of him in single-season batting average in all of recorded baseball history, one person since Williams has done so with at least 200 plate appearances, and that was Josh Gibson, who played his career in the Negro Leagues. In other words, many things are possible, but sustaining something is much harder to do than achieving it one time out of many attempts. That's the intuition behind the need for sample size. A guy could play his first Major League Baseball game and go 2 for 5, but that doesn't make him the next Ted Williams. If he goes 200 for 500, now we're talking. Sample size is a meaningful concept, and it helps put a brake on some of our natural tendencies to extrapolate. But sometimes, sample size concerns can act as a way of letting us ignore interesting new information, and what I'm going to show you is a simple demonstration of the fact. This demonstration comes from Chapter 3 of How to Measure Anything, in which Douglas Hubbard takes us through a simulated scenario. The idea is simple. You have an urn containing marbles. You don't know anything about the urn, except that it has some large number of marbles, and each marble is one of 2 different colors. It's either blue or orange. Hubbard uses red and green, but I'm switching it up a little to avoid potential visual confusion. The only piece of information you will receive is that you get to pull one marble out of the urn. Then, based on that one marble, your job is to guess whether the majority of marbles in the urn are blue or orange. Sounds impossible, right? I mean, we could easily pull a single blue marble out of a sea of orange marbles and guess totally wrong. It turns out, however, that in this scenario, you can go from a 50% probability of getting the right answer to almost 75% probability with that one new piece of information. In the show notes, I'll have a link to a derivation of this, but in the meantime, let's go to the demo and see it in action. We are in Excel. I have a copy of Douglas Hubbard's spreadsheet open, showing the intuition behind this phenomenon. In this scenario, Hubbard has 1,000 data points. In column A, we have the urn number. There are 1,000 total urns, so we perform the simulation 1,000 times. In column B, we have a randomly generated percentage representing the percentage of green marbles versus red marbles. The percentage of red marbles is necessarily 100% minus the percentage of green marbles. Column C simplifies the scenario, showing which of the 2 is the majority color. If the percentage of green marbles is greater than 50, then we display green. Otherwise, we display red. That means that, in the event we land on exactly 50%, we say red rather than a tie. But that doesn't change the math in any significant fashion. In column D, we randomly draw a marble, either green or red. Finally, column E checks to see if the values of columns C and D match exactly. If so, we write out yes. If not, we write out no. And the cell E5 shows us the percentage of times that we drew a color that was the same as the majority color. Starting out, this number is 75%, which is what I told you in the intro. If you want to run this simulation multiple times, Excel has a shortcut to recalculate formulas, F9. I'll press F9 several times here, and we can see that the share stays around 75%. Maybe it goes up to 76 or 77, maybe down to 73, 72, but we don't see a radical departure. And this is a pretty neat result, but now I'm going to show you how you can recreate this demonstration in Python. This is a simple Python script that performs the same calculations as in Excel. It is about 50 lines of code, but in fairness, half of that is comments, new lines, and print statements. We're going to use the random function in the random library. This generates a floating point number between 0 and 1, and the function follows a uniform distribution. In other words, there is an equal likelihood of pulling any value from the range. Ignoring that entire bit about the probability of any point value in a continuous distribution being 0, and let's just think about infinitesimally small ranges of values, if that helps you sleep better at night. Anyhow, jumping down to line 34, we are going to start with 5 trials, just so we can see how everything's working. Later on, we'll stand up 1,000 trials, like we did in the Excel spreadsheet. On line 37, we generate our 5 urns. For each urn, we define how many blue marbles we have and how many orange marbles we have. In this case, it's pretty simple. The percentage of blue marbles is the same as 100% minus the percentage of orange marbles. If we have 10 or fewer urns, we'll print out the probabilities for each urn for diagnostic purposes. If we have more than 10 urns, that's just going to give us too much information in the console, so I won't print out the list. After that, on line 39, we describe the urn using the colorize function. Jumping back up to line 3, we can see that colorize takes one parameter, x. If x is less than 0.5, we say that this is a blue majority urn. If it is 0.5 or greater, we say that this is an orange majority urn. That's a very simple function and is only here for our convenience. Going down to line 43, we now draw one marble from each urn using the draw function. We define the draw function on line 14, where we call random yet again. This time, if the result of random is less than p, we return true. Otherwise, we return false. In case you're a little confused about why we're returning random less than p, it's important to remember that we are doing 2 independent calculations. The first calculation is, what is the distribution of blue versus orange marbles in the urn? The p parameter that we send into the draw function is the percentage of orange marbles. If p is 0.2, for example, we call this a blue urn, but p still represents the percentage of orange marbles, regardless of what we call the urn. Then we generate a random number along that uniform distribution. If 20% of our marbles are orange, we would only draw an orange if the random number is below p. Otherwise, that marble is blue. Going back down to line 45, we can then generate a color by passing in the result of our draw. Our draws are true and false, and converted to floating point numbers, those are 1 and 0. Remember that draw tells us whether we have pulled an orange marble, so 1 represents an orange marble, 0 represents a blue marble. Returning to the definition of colorize, this function definition still happens to work. Blue if x is less than 0.5, orange if 0.5 or greater. Now we can determine how many successful predictions we had. I have a list of trial colors and a list of draw colors. I'm going to zip those 2 lists together. That's a fancy term for saying that I'll take the first element from the first list and pair it with the first element of the second list. Then I'll take the second element from the first list and pair it with the second element of the second list. I'll take the third element of the first list and pair it with the third element of the second list, and so on through all elements in both lists. This gives me tuples, whose elements I'm calling trial and draw. I pass these to the successful prediction function, which we define on line 23. This is a simple helper function that returns true if the trial color matches the draw color, or false if they disagree. With those successful predictions, I can generate a successful prediction ratio, taking the sum of successful predictions, which logically is the same thing as the count of list elements whose value is true, taking that and dividing it by the number of trials. Finally, on line 52, we print out the results. Let's see how this works. In the terminal, I'm already in the directory with my code and have already run Python once, executing the code in earnofmystery.py. Because I have fewer than 10 trials, we see some diagnostic information. I'm showing you this pre-calculated set so we can easily talk about it, but I will give it a couple more runs afterward just to prove that everything works the way we expect. In this case, we ran 5 trials. We see 5 different probabilities that happen to be ascending in this scenario. That just turned out that way. The first 2 probabilities of orange marbles are below 0.5, so we label those as blue urns. The next 2 are right around 0.5, but they're both slightly over, so we label them as orange. Finally, the last probability is 0.66, so it is clearly an orange urn. After that, we draw 1 time for each urn. We pulled 1 orange, 3 blue, 1 orange. Comparing that to blue, blue, orange, 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 we can see that only 2 of the pairs are in agreement, the second and fifth urns and their respective marble draws. The other 3 disagree, so our successful prediction percentage in this case is a meager 40%. Now, I've run this other times in the past and have ended up with other numbers. To prove it, let's run this a few more times and, well, you can see just right now how the percentages change. In practical terms, there are only 6 possible outcomes to this scenario. No matches, followed by 1, 2, 3, 4, or 5 matches. Let's spice things up a bit by increasing k to 1,000. I can do so by modifying line 34, changing the value to 1,000. Now, when I run this a few times, we can see that we stabilize right around a 75% success rate, but we're floating around that range, just like we did in Excel. This means maybe if I increase the sample, it'll tighten up further. So let's do that. I'll increase the number to 100,000 for K, and this time around, we are nailing 75% each time, and that's not a bad result at all. That was a quick demonstration of the urn of mystery. In real life, there are a few scenarios in which this can be interesting. First, imagine A/B testing a website or product. We start from the basis that there's an equal likelihood that each product will be the better one, as we don't know and we want to eliminate our own biases, pushing toward A or B. We can then ask a person at random. That person's response can change our expectations of whether A or B is better, assuming we do a good job of picking someone at random. Similarly, if you're canvassing interest in a political candidate, randomly contacting a single person can narrow down which candidate is likely to be the more popular one. Or even, let's say that you're trying to figure out where to go for dinner, and you've narrowed it down to 2 places, Restaurant A and Restaurant B. You haven't been to either one of these, so you don't have a strong opinion on them. Therefore, ask a random person, and if that person says A is definitely better than B, well, there's a pretty good chance that you'll agree after you try them both out. But before we go, I do want to warn you that this outcome relies on 2 important assumptions. First, we assume that there are exactly 2 options. In real life, we rarely have 2 clear-cut options. You can vote for candidate A, or vote for candidate B, or you could vote for some minor party candidate C, or write in your dog's name, or even abstain from voting. Once you introduce that level of complexity, the results are nowhere near as clear-cut. Second, we assume that we pick someone at random. Any bias in how you select your sample can affect your results. Going back to the political example, if it is significantly easier to pick up somebody who supports candidate B, and maybe the people who support candidate A are a lot cagier about sharing their opinions or they're harder to get a hold of, in that case, you may artificially inflate candidate B. Or let's say that you perform some A/B test and call up your mom, who you've been keeping up to date on the great work you've been doing on this product. Well, she'll probably be more likely to say that she likes the work you did versus the alternative. Finally, with just one data point, we go from a coin flip to approximately 75% chance of success. 75% may or may not be good enough for what you need. If we're talking about some low-cost thing, like choosing between going to 2 places for dinner, this might be enough to push you toward one of those options. But if you're thinking about investing millions of dollars in a new product line, maybe ask more than one person before you do it. And that takes me to the final point. This simple example covers the most extreme scenario, from zero information to minimal information. It turns out that, with a very small sample size, you can get close to actual results very quickly. That is, within a few data points. But for that explanation, you're going to have to pick up a copy of the book. We'll have links and show notes in the description below, and until we see each other in the next video, take care.